Hello, everyone, and welcome to Kognito Key. I am so excited you're here today because we're diving into something truly mind-bending in the world of electronics. Have you ever wondered how we can actually force electrons to break the traditional rules of classical physics just to build faster technology? Well, in today's explainer, we're going to unlock the quantum magic behind tunnel diodes. It's a really colorful, absolutely fascinating journey down into the microscopic world. So let's just get right into it. Okay, so what exactly is a tunnel diode? Basically, it's a heavily doped two-terminal semiconductor device. But here is the truly wild part. Instead of electrons having to climb over an energy barrier like they would normally have to do, they literally punch straight through it. Because the depletion region inside is so incredibly thin, the electric current flows through this amazing process we call quantum mechanical tunneling. I mean, these electrons are penetrating the barrier at speeds that are somewhat similar to the velocity of light. How cool is that? Now, you're probably asking yourself, how is this actually different from a standard normal diode? Well, a typical diode usually uses silicon, right? It has a relatively low doping concentration and a fairly wide depletion region. But our tunnel diode, it is built completely differently. It relies on materials like germanium or gallium arsenide. We don't use silicon here because its ratio of peak to valley current is just way too low. And more importantly, we dope the tunnel diode 1,000 times more than a normal diode. It's that extreme doping concentration that creates the ultra-thin depletion region, which is what makes the whole tunneling effect possible in the first place. So who exactly do we have to thank for this massive breakthrough in physics? We actually have to travel back to the year 1957. Dr. Leo Esaki is the brilliant mind who invented this remarkable device. And because of his pioneering work, you'll often hear the tunnel diode referred to in the engineering world as the Esaki Diode. But let's think about this from the perspective of a single electron. How does it actually experience this quantum tunneling as we mess around with the voltage? Imagine the journey of just one electron trying to navigate through varying voltage levels. To really wrap our heads around this magical behavior, we need to take a close look at its voltage current, or VI, characteristics. Let's walk through the four main stages of how it operates. First up, we have the zero-biased condition. When there's no applied input voltage, electrons are just tunneling equally in both directions because of temperature, which means there's no net current flowing. Then, for step two, we apply a small forward voltage. Even though it is less than the barrier potential, those electrons in the conduction band just punch right through to the valence band, giving us a small forward current. In step three, we crank up the voltage a bit more. The energy bands become perfectly parallel, and that allows the absolute maximum number of electrons to tunnel through. This right here is where we hit our highest or peak current. But then comes step four. If we increase that forward potential even further, the bands actually start to misalign. That overlapping connection drops off, and surprisingly, the tunneling current begins to decrease. And that sudden drop, that brings us to one of the most counterintuitive concepts in electronics, negative resistance. This is a highly unique characteristic where the current flowing through the device actually goes down, even when the applied voltage is going up. In classical physics, more voltage almost always means more current. But here, the current just plummets all the way down until it hits its absolute lowest value, which we call the valley point, or valley current. This right here is the true defining magic of the tunnel diode. So what happens if we just keep pushing the voltage up right past that valley point? Well, normal diode behavior simply kicks back in. Once the applied forward voltage gets high enough to completely overcome the barrier potential of that depletion region, the quantum tunneling stops entirely. From that exact point onward, the device just acts like a regular old PN junction diode, with the current increasing normally as you turn the voltage up. Of course, in the real world, this unique behavior comes with some very distinct pros and cons. On the plus side, tunnel diodes are fantastic because they consume very low power, they're really inexpensive to make, and they provide extremely high-speed operation. I mean, remember, those electrons are punching through almost at the speed of light. But on the flip side, we do have to mention a couple of drawbacks. Those abrupt changes in load current with the applied voltage can be tricky to manage. Also, since it's just a simple two-terminal device, you don't really get proper isolation between your input and output terminals. So where do we actually use these? Because of that incredibly fast response time, tunnel diodes are absolute magic for specific real-world tech. They are heavily used in microwave applications and high-frequency environments. You're going to find them acting as really crucial components in amplifiers and in oscillator circuits, basically working behind the scenes to help make our modern high-speed communication systems run smoothly. It is just so amazing to see how quantum mechanics literally shapes the technology we use every day, letting us bend the rules of physics to build faster and more efficient devices. I really hope this explainer helped you get a clear picture of the fascinating world inside tunnel diodes. If you enjoyed this journey and want to unlock even more concepts with our colorful explainers, please hit that subscribe button to join us here at Kognito Key. And don't forget to like and share this video with your friends. As we keep pushing the limits of technology, it definitely makes you wonder, what other rules of classical physics are we going to break next to power the future? Thank you so much for watching, and as always, stay curious.